Before the journey unfolds, let me ask you something. When you look at the world around you, do you ever wonder whether the solid and familiar things you trust are only shadows of a deeper structure you never directly see? What if every grain of matter carries many quiet possibilities that never appear in your everyday experience, yet still shape every event around you? Why does a single electron behave as if it walks through many paths at the same time? Why do paired particles behave as if they share a hidden understanding that stretches across entire continents without sending any message at all? And if the smallest pieces of nature do not obey the rules of common sense, what does that reveal about the universe we live in? The story begins more than a century ago, when scientists expected the universe to be a calm and predictable place, governed by familiar rules. Classical physics seemed complete. It explained falling apples, spinning wheels, the motion of planets drifting in calm orbits around the sun. Every event had a cause. Every outcome was determined. The world appeared solid, mechanical, and neatly ordered. Yet hidden deep within the glow of heated metals and the delicate shimmer of light itself, something refused to fit the classical mold. When researchers tried to explain the way a heated object emitted light, they discovered that classical equations predicted an impossible result. They claimed that a simple piece of metal should radiate infinite energy at short wavelengths. No one could accept such a contradiction. The natural world clearly did not explode with infinite brightness. Something was wrong with the classical picture. At the dawn of the 20th century, Max Planck made a reluctant proposal to repair the failing theory. He suggested that light could not be emitted in arbitrary amounts, but only in small packets that came in discrete steps. This idea felt strange and uncomfortable, yet it matched observations with uncanny accuracy. A few years later, Albert Einstein pushed the idea further when he explained the photoelectric effect. He showed that light striking a metal surface behaved as if it were made of individual particles that carried energy in precise chunks. This explanation was not speculation. It came directly from measured data. The energy of the ejected electrons depended only on the color of the incoming light, not its brightness. Classical physics could not explain it. Einstein's photon interpretation could. These breakthroughs forced scientists to look at light and matter in a new way. Light, once thought to be a smooth wave, behaved like a particle. Electrons, once thought to be tiny hard balls, created patterns of interference when passed through narrow slits. Patterns that only waves should produce. It began to appear that the fundamental ingredients of the universe did not fit neatly into either category. They were neither classical particles nor classical waves. They were something else entirely. This strange behavior raised deeper questions. When an electron passes through two narrow openings carved into a barrier, the resulting pattern on the screen beyond it resembles a series of bright and dark bands, a sign of wave interference. Yet when detectors are placed near the openings to check which path the electron takes, the interference vanishes. It seems that the very act of detection forces the electron to behave like a particle. When left alone, it behaves like a wave. When observed closely, it settles into a single outcome. What kind of entity can switch its nature based on how we examine it? Scientists realized that classical intuition could no longer guide them. They needed a new framework, one built not on fixed trajectories, but on probabilities and something even more subtle. Instead of describing where a particle is, this new framework described every possible state it could occupy at once, weighted by complex numbers called probability amplitudes. These amplitudes were not probabilities themselves. They were deeper quantities that carried both magnitude and phase. When they combined, they produced the interference patterns seen in countless experiments. The mathematics suggested that a particle did not simply choose a single path. It existed in a combination of possibilities that could merge or cancel depending on the circumstances. This idea, unsettling at first, was not speculation. It came directly from measurements repeated across generations of scientists. Every time researchers sent single electrons or single photons through an interferometer, the outcome pointed to the same conclusion. Nature, at its smallest scales, works through amplitudes, not through fixed properties. Only when a measurement is made do these amplitudes translate into definite outcomes, according to a precise rule known as Born's rule. This principle, tested in laboratories around the world, has never failed. It forms the backbone of modern quantum mechanics. Yet this shift from certainty to probability created tension. Classical probabilities represent ignorance. If you flip a coin, the coin already has a definite result before it lands. You simply do not know it yet. But in quantum mechanics, the probabilities do not arise from hidden details. They arise from the structure of the quantum state itself. Before measurement, the particle truly exists in multiple possibilities at once. This was not an opinion or a philosophical argument. It was what the experiments demanded. As the classical picture lost its grip, the path toward quantum mechanics grew unavoidable. The microscopic world would not stay silent. It revealed clues that pointed toward a deeper truth, a truth that challenged even the most confident expectations of classical thought. Step by step, experiment by experiment, scientists accepted that the smallest parts of reality do not behave like miniature versions of everyday objects. They obey principles rooted in amplitudes, waves of possibility, that guide their behavior until the moment they are measured. And as these discoveries settled into scientific understanding, a new question formed. If the world is built from amplitudes, what other phenomena arise from this structure? How does a single system explore multiple states at once? And what happens when more than one system becomes linked in ways that stretch far beyond classical notions of cause and effect? The deeper scientists pushed into the microscopic world, the clearer it became that the familiar rules of classical physics could not explain the strange and delicate patterns emerging from experiment after experiment. Every attempt to force quantum behavior into classical frameworks failed. Electrons did not travel along single sharp paths. Photons did not behave like tiny billiard balls. Matter did not remain confined to precise positions and speeds at the same time. These realizations were not philosophical debates. They were direct lessons from laboratory data. The universe at small scales refused to be boxed into the comforting logic that governed apples falling from trees or planets circling the sun. Instead, nature seemed to whisper that reality was built from a quieter and more fluid language, one in which possibility held as much weight as certainty. In this new landscape, the concept of a quantum state became the central pillar. It was not a location in space and not a set of hidden instructions. It was a complete description of everything that could possibly be known about a particle. This state contained the amplitudes that described every allowed configuration. And these amplitudes combined with one another in ways that classical thinking never anticipated. When an electron encountered a barrier with two openings, the amplitude describing the left path and the amplitude describing the right path did not compete. They intertwined, creating a pattern that only revealed itself across many repeated measurements. Each electron struck the screen one point at a time, yet the overall pattern built from these points contained the unmistakable signature of interference. Even when sent through the apparatus one by one, never interacting with any other electron, the pattern still emerged. This showed that the behavior did not come from collisions or hidden influences. It came from the structure of the quantum state itself. Measurements, however, displayed a completely different face of this strange world. The moment a position or a path was measured, the delicate wave of possibilities collapsed into a single definite outcome. The mathematics predicted this sudden reduction, and experiments confirmed it with unwavering consistency. When detectors were placed to determine which path the electron took, the interference vanished entirely, and the electron behaved as if it had walked through only one opening. This suggested that measurement was not merely passive. It was an interaction that forced nature to choose a definite result from its silent collection of possibilities. The rules governing these results were strict and predictable. The probability of each outcome corresponded exactly to the square of the amplitude associated with that possibility. This rule, proposed by Max Born, has been tested in countless experiments and remains one of the most precise laws in science. As this new framework solidified, scientists realized that the classical picture of nature was only an approximation. It worked well for large objects where quantum effects were washed out by countless interactions with the environment. But at small scales, where isolation was possible and disturbances could be controlled, the quantum rules stood tall and unmistakable. The universe did not switch from classical to quantum. It had always been quantum. Classical physics simply described the behavior that emerged when enormous numbers of quantum particles acted together. In that collective setting, the strange interferences of individual amplitudes cancelled out or became too subtle to detect, giving the comforting impression of solid objects with definite properties. This realization helped scientists understand why the world feels predictable, even though its foundation is built from probabilities. When trillions of particles interact with their surroundings, the delicate coherence of their quantum states fades quickly. This process, known as decoherence, explains why large objects do not display quantum interference in daily life. It is not because quantum rules stop working. It is because the environment constantly interacts with them, wiping away the fragile patterns that define quantum behavior. Decoherence does not require speculation and does not depend on philosophical interpretation. It is a measurable effect observed in laboratories where researchers cool atoms to near absolute zero or isolate superconducting circuits inside vacuum chambers to protect their quantum states. As more experiments confirmed the predictions of quantum mechanics, the confidence in this new theory grew. It explained the stability of atoms, the formation of chemical bonds, the behavior of semiconductors, and even the nuclear processes that power the stars scattered through the sky. Every triumph reinforced the idea that the universe at its core is not built from small hard objects but from mathematical structures that describe possibilities combining and interfering. This new understanding did not replace common sense, but rather expanded it, revealing that the rules governing the smallest pieces of nature demand a broader and more flexible intuition. Yet as powerful as this framework was, another question emerged that would push quantum theory into even stranger territory. If a single particle could exist in many possible states at once, what happened when two particles interacted? Could their possibilities become linked in a way that went beyond anything classical physics allowed? Could the outcome of one particle be tied to the outcome of another, even if they were separated by great distances? Experiments soon showed that this was not only possible, but unavoidable. The moment two particles shared a quantum interaction, their combined state contained correlations that no classical explanation could reproduce. These correlations did not involve messages or signals. They were woven into the structure of the shared quantum state itself, a feature that would later be known as entanglement. As the 20th century unfolded, the stage was set for one of the most profound discoveries in science. Superposition revealed that individual particles hold multiple possibilities at once. Entanglement revealed that multiple particles can share possibilities in ways that bind their outcomes together. Both phenomena grew directly from the same mathematical foundation. Both were confirmed by relentless experimental work. Both shaped the modern understanding of the quantum world. The growing recognition that quantum mechanics described a world of possibilities rather than fixed trajectories marked a profound shift in human understanding. Yet throughout this transformation, scientists remained anchored to one guiding principle. Every claim had to be supported by experiment. Every idea had to be tested against the behavior of real particles, real atoms, and real light. This discipline allowed quantum mechanics to mature into the most accurately verified theory in the history of science. Predictions drawn from its equations matched experiments with extraordinary precision. Atomic spectra lined up with theoretical values. The behavior of electrons inside metals followed patterns dictated by quantum rules. Even the energy levels of hydrogen matched the mathematically predicted structure to an astonishing degree of accuracy. No competing framework came close. But precision alone did not soften the sense of mystery that quantum mechanics introduced. The equations worked, yet many of their implications challenged deeply held assumptions about the nature of reality. Classical physics taught that objects have definite properties, whether or not we measure them. Quantum mechanics showed that some properties do not exist in a definite form until the moment of measurement. This did not mean that reality vanished. It meant that reality at small scales is expressed in the language of amplitudes rather than fixed values. The measurement did not uncover a hidden property. It created a definite outcome from a spectrum of possible ones. This idea troubled many of the greatest thinkers of the 20th century, yet experiment after experiment supported it with unbroken consistency. Among the earliest challenges to this new worldview came from the structure of the atom. Classical physics predicted that electrons orbiting a nucleus would radiate energy and spiral inward, collapsing the atom in a tiny fraction of a second. Yet real atoms are stable. They do not collapse. They persist for billions of years. Quantum mechanics resolved this puzzle by showing that electrons do not orbit in classical paths. Instead, they exist in standing wave patterns around the nucleus, each pattern corresponding to a specific energy level. These patterns do not radiate energy because they are stable solutions to the Schrödinger equation. They are not little planets circling a little sun. They are distributions of probability spread out in space. This insight was not metaphoric. It was based on the mathematics that correctly described atomic spectra observed in laboratories across the world. The strangeness extended further when scientists probed smaller and smaller phenomena. Electrons confined inside tiny regions displayed discrete energy levels. Atoms cooled to near absolute zero behaved as if they were a single wave of matter spanning many micrometers. Superconducting materials allowed electrons to move without resistance, a feat impossible in classical physics. Every one of these behaviors arose directly from quantum mechanics. None required speculation. All were supported by repeated observations and carefully controlled experiments. The more quantum mechanics succeeded, the more scientists were forced to abandon classical intuition. Even familiar ideas such as position and momentum took on new meanings. It became impossible to define both with arbitrary precision at the same time. This was not a limitation of measurement devices. It was a fundamental feature of nature described by the uncertainty principle. Measurements that pinned down position blurred momentum, and measurements that pinned down momentum blurred position. The principle did not arise from missing information or from hidden variables waiting to be uncovered. It arose from the wave-like structure of quantum states themselves, a structure that had already been verified through interference experiments that left no room for classical interpretations. As the edges of classical certainty crumbled, the quantum framework stood tall and unshaken. Its predictions spanned an enormous range of scales. It explained how electrons behave inside the silicon chips used in computers. It described how atoms form molecules and how molecules interact to create the chemical reactions that shape life. It accounted for the radiation emitted by stars and the fusion processes that allow the sun to shine steadily for billions of years. The successes of quantum mechanics were not confined to the laboratory. They were written directly into the fabric of the universe. Yet despite this broad explanatory power, one fundamental idea remained at the heart of all quantum behavior. The world is built not from single possibilities, but from combinations of possibilities. A quantum state can hold many allowed configurations at once, each carrying its own amplitude. These amplitudes are not abstract decorations. They are the essential pieces that determine how particles behave when they move, interact, or encounter obstacles. The interference of amplitudes produces the patterns seen in diffraction experiments. The collapse of amplitudes under measurement produces definite results. The linearity of amplitudes underlies everything from atomic structure to the behavior of superconducting circuits. Superposition is not an option added onto physics. It is its foundation. This realization forms the final step in understanding why quantum mechanics could not remain a minor correction to classical thinking. It represented a complete shift in perspective. The classical world of trajectories and forces was a shadow cast by the deeper quantum world of amplitudes and probabilities. Every classical event arose from quantum behavior averaged over immense numbers of particles. Every certainty emerged from a foundation of microscopic uncertainty. Quantum mechanics did not simply challenge the classical picture, it replaced it with a more complete description that embraced both the predictable and the probabilistic. By the time the first quarter of the 20th century had passed, the essential pieces of quantum theory were in place. They revealed a universe more intricate and more subtle than anyone had expected. But as powerful as these ideas were, they hinted at something even more extraordinary. The structure of a single quantum system was strange enough, yet the structure of two systems taken together would open a door to a phenomenon that seemed almost impossible at first glance. A phenomenon that would push the boundaries of physics, challenge the minds of Einstein and Bohr, and eventually transform technology itself. With the framework of quantum mechanics established and the classical worldview reshaped by evidence, the path now leads naturally to the next chapter. It is here that the quantum state takes on its full meaning. It is here that the nature of possibility is revealed, not only within a single particle, but woven between many. And it is here that superposition prepares the stage for the phenomenon that would come to define the deepest mysteries of quantum reality. The moment scientists accepted that classical rules could not describe the microscopic world, they faced a new question that demanded careful thought. If particles did not follow fixed paths or carry well-defined properties before measurement, then how exactly should their behavior be represented? What kind of mathematical language could capture a world built from possibilities rather than certainties? The answer arrived through a delicate interplay of intuition, experiment, and the relentless search for equations that matched observed data. What emerged was the idea of the quantum state, a concept that reshaped the foundations of physics with quiet but irresistible force. In classical physics, the state of a system is nothing mysterious. It is a list of measurable properties such as position, momentum, and energy. These quantities may change over time, but at any instant they are assumed to have definite values whether or not anyone attempts to measure them. A marble rolling across a floor does not need to be observed to possess a location. But quantum mechanics demanded a different kind of description, one that went beyond listing properties and instead embraced the entire range of possibilities a system could explore. The quantum state did not represent where a particle was. It represented everything the particle could be, weighted by amplitudes that carried both size and phase, quantities that determined how these possibilities interacted. This idea might have seemed abstract, were it not for the steady stream of experiments that forced it into existence. When electrons created interference patterns even when released one at a time, the classical picture of definite paths vanished. When photons behaved like waves in one apparatus and like particles in another, the idea of fixed traits collapsed. The only consistent explanation was that particles were described not by definite properties, but by a wave-like state that spread out across space, interacting with itself and producing measurable consequences. This wave was not a physical object like water rippling across a pond. It was a mathematical representation of all possible outcomes encoded in amplitudes. These amplitudes predicted where a particle was likely to appear without claiming it was already in one exact place. To express this new perspective, scientists turned to the language of vectors and spaces. They discovered that the quantum state behaved like a vector inside a mathematical structure called a Hilbert space. This space was not a physical region, but an abstract landscape where each point represented a possible configuration of the system. Just as a direction in ordinary space can be represented by combining basis directions, a quantum state could be represented by combining basis states. The coefficients of this combination were the amplitudes that determined the probability for each measurable outcome. This representation captured every feature revealed through experiment. It explained interference, measurement, energy levels, and the behavior of systems over time. The evolution of the quantum state followed its own precise rule. Erwin Schrödinger introduced an equation that predicted how a quantum state changed from moment to moment. This equation was not guessed from philosophical speculation. It was built to match the observed behavior of atoms, electrons, and photons. When applied to the hydrogen atom, it produced energy levels identical to those measured in laboratory spectra. When applied to particles encountering barriers or potential wells, it predicted patterns of reflection, transmission, and resonance that agreed with experiment. Over decades of testing, the Schrödinger equation proved to be an extraordinarily accurate tool, capturing the dynamics of countless systems with remarkable precision. Yet as powerful as this equation was, it carried an essential distinction that separated quantum mechanics from classical physics. In classical systems, probabilities arise from ignorance. A coin has a definite outcome even before it lands. We simply do not know it. In quantum mechanics, probabilities arise from amplitude interference. The quantum state evolves smoothly and deterministically according to the Schrödinger equation, but the outcomes of specific measurements appear only when an interaction forces the amplitudes to collapse. This collapse is not a flaw or a mystery hidden behind metaphysical curtains. It is an operational rule that explains how experiments behave and is supported by every measurement ever made. The world at small scales is expressed through amplitudes until a measurement forces a definite result. Because the quantum state encompasses all possible outcomes, it must be described with extraordinary care. Sometimes the state represents a system in a single coherent configuration. Sometimes it represents a statistical mixture of several possibilities. Scientists distinguish these by using a mathematical object called a density matrix, a tool that captures both pure states and mixtures. Pure states describe systems with full quantum coherence, systems that can produce interference. Mixed states describe systems where coherence has been lost, often through interaction with the environment. This distinction, though subtle, is essential. It helps scientists understand why quantum effects appear in isolated atoms, but vanish in warm, macroscopic objects. The structure of the state also depends on the basis used to describe it. In one basis, a particle might appear in a definite energy level. In another, it might appear as a combination of different positions or momenta. The ability to switch between these bases is not a trivial trick, but a fundamental feature of quantum mechanics. Different experimental setups reveal different aspects of the same quantum state. A system that looks simple in one measurement basis can look deeply complex in another. These transformations are not philosophical interpretations. They are mathematical operations grounded in laboratory procedures that have been performed countless times. As this understanding deepened, scientists realized that the quantum state was more than a tool. It was the central object of the theory, the full description of what could be known about a system before measurement. It captured all possibilities, encoded all outcomes, and guided how these outcomes could interfere with one another. The classical idea of a particle carrying fixed properties faded into the background. What remained was a flexible, dynamic, and deeply structured entity that revealed its nature only when asked the right question by a carefully designed measurement. The stage was now set for one of the most profound consequences of this framework. If a single quantum system could hold many possibilities at once, then multiple systems taken together could hold possibilities that intertwined in ways far beyond classical intuition. When two quantum states meet, the amplitudes describing their individual possibilities combine into a larger structure that describes them jointly. This structure can contain correlations that do not exist in any classical description. These correlations do not arise from hidden signals or communication. They arise from the way amplitudes merge inside the larger state. This merging opens the door to superposition in single systems and to entanglement in combined systems, two phenomena that lie at the heart of quantum mechanics. As scientists continued exploring the structure of quantum states, they discovered that the mathematical framework carried a remarkable elegance. Every possible configuration of a system could be expressed as a combination of basis states, and the choice of basis played a crucial role in how the system appeared when measured. In the position basis, the quantum state revealed how the probability of finding a particle varied across space. In the energy basis, the state revealed the stationary patterns that governed atomic levels and chemical bonds. These different descriptions did not contradict one another. They were simply different ways of viewing the same underlying reality, much like rotating a sculpture to see new contours without altering the sculpture itself. Understanding these transformations was essential because quantum systems responded differently depending on the type of measurement performed. A system prepared in a definite energy state would remain in that state until disturbed. Yet the same system could exhibit a wide spread of possible positions if examined in the position basis. Conversely, a particle localized in a narrow region of space would display a wide range of possible momenta. This interplay between basis choices reflected a deeper truth about quantum mechanics. No single set of properties provided a complete picture. The full description lived in the amplitudes themselves, and measurement simply picked out one aspect of that rich structure. To see how this worked in practice, consider an electron trapped inside a potential well, a tiny region where the particle is confined by surrounding forces. The Schrödinger equation predicts that the electron cannot simply possess any energy it wishes. Instead, it must adopt one of a discrete set of energy levels, much like notes on a musical instrument. These levels arise from the requirement that the wave describing the electron must fit inside the well in a smooth and continuous way. Experiments confirm this quantization with extraordinary precision. When electrons transition between these levels, they absorb or emit light in fixed amounts corresponding to the difference between energies. This phenomenon forms the basis of atomic spectroscopy and provides one of the most direct pieces of evidence that quantum states carry real physical meaning. Yet the quantum state is not limited to describing confined particles or simple setups. It applies equally well to free electrons drifting through space, to photons streaming from distant stars, and to atoms cooled to temperatures near absolute zero. In each case, the state captures the full range of possibilities available to the system. For free particles, the state describes how likely they are to be found in different places or to possess different momenta. For photons, the state reveals how their polarization or frequency might be observed. For ultra-cold atoms, the state can describe extended matter waves that stretch across regions much larger than the atoms themselves. In every situation, the predictions of quantum mechanics match experiment after experiment, reinforcing the idea that the quantum state is not a mathematical convenience, but a faithful reflection of nature at its smallest scales. One of the most intriguing aspects of quantum states is their tendency to evolve smoothly when not measured, yet change abruptly when a measurement occurs. The deterministic evolution, governed by the Schrödinger equation, can be visualized as a gentle unfolding of amplitudes over time. Peaks shift and spread. Valleys deepen or flatten. The state flows like a silent cloud of possibilities, guided by the potential landscape in which the particle moves. But the moment a measurement interacts with the system, this cloud collapses into a definite result. The collapse is not a physical explosion or a sudden physical movement. It is a transition in the information we can assign to the system, enforced by the fundamental rules of quantum mechanics and confirmed by the outcomes observed in experiments. The measurement does not reveal a hidden property. It triggers a change in the state that aligns with the observed result. This distinction between smooth evolution and abrupt collapse raised many questions, and it continues to be discussed in philosophical circles. But the operational facts are simple and unambiguous. The Schrödinger equation governs the evolution of the state before measurement, and the Born rule governs the probabilities of outcomes when measurement occurs. This combination has passed every test devised by generations of physicists. It is the foundation upon which quantum technologies are built, from lasers to superconducting qubits. to precision atomic clocks. These devices operate with astonishing accuracy because the quantum state captures real physical behavior, not imagined abstractions. The mathematics also reveals something subtle but essential. When two quantum systems are combined, their joint state is not obtained by simply adding their individual states. Instead, the combined state is built through a mathematical operation that creates a larger space containing every possible combination of the individual states. This new space is called the tensor product space. It is here that the door opens to entanglement. But before entanglement can be understood, one must appreciate that even simple combinations of quantum states produce rich and sometimes surprising structures. When two systems exist together, their possible configurations expand dramatically, and the amplitudes describing one system can become intertwined with those describing the other. Nothing like this exists in classical physics, where the state of a combined system is simply the list of states of its parts. Quantum mechanics requires a deeper and more interconnected description. This interconnected structure is evident in multiple experimental setups. When particles interact, their quantum states merge in a way that preserves all the information carried by the separate states, while creating new possibilities that did not previously exist. These new possibilities reflect correlations that cannot be described by assigning independent properties to each particle. Instead, the particles share a joint state that encodes how their outcomes relate to one another. Even when separated after the interaction, the structure of their combined state remains. Measurements performed on one particle reveal patterns that are linked to measurements on the other. These correlations do not violate relativity. They do not transmit messages faster than light. They simply reflect the structure of the quantum state created during the interaction. As scientists work to understand these ideas more deeply, they refined the tools used to describe quantum states. Density matrices allowed them to capture both pure and mixed states. Operators allowed them to represent measurements and transformations. Projection rules allowed them to calculate how states collapse after measurement. Together, these tools formed a coherent mathematical framework that described everything from the simplest particles to complex many-body systems. The framework was not imposed on nature. It was drawn directly from observation. By the mid-20th century, the quantum state had become the undisputed centerpiece of microscopic physics. It revealed a reality built not from fixed traits, but from possibilities woven into delicate patterns of amplitude and phase. It described systems that changed smoothly until observed and that responded to measurement in ways far beyond classical expectation. And it provided the blueprint for the next great conceptual leap in quantum theory. A leap that would connect systems across distances, create correlations impossible in classical worlds, and reshape our understanding of the boundary between one and many. As quantum mechanics matured into a reliable and experimentally verified theory, the role of the quantum state grew clearer with every passing decade. It was no longer seen as a temporary mathematical construction, but as the essential carrier of information about any physical system. Everything that could be predicted about a particle or a group of particles came from its quantum state, expressed through amplitudes that governed how likely different outcomes would be observed. These amplitudes were not mere placeholders. They interfered, evolved, and transformed in ways that shaped real physical phenomena. Their presence became the trademark of quantum behavior itself. One of the most important lessons drawn from this understanding was the realization that quantum states do not simply sit quietly waiting to be measured. They evolve continuously, even when unobserved. A particle drifting in space changes its state as naturally as a river follows its course. The shape of its amplitude distribution spreads out or narrows depending on the forces it encounters. Light traveling across the vacuum does not hold a fixed configuration. Its state evolves according to the same rules, carrying information about polarization and frequency. This dynamical nature of the quantum state reveals how deeply time and possibility intertwine. It shows that the frameworks of classical mechanics are merely approximations that emerge when quantum evolution becomes averaged over large scales. The implications of this dynamical structure extend to every corner of physics. The stability of atoms depends on stationary quantum states that do not change their energy over time. The creation of chemical bonds arises from quantum states shared between electrons on neighboring atoms. The functioning of lasers relies on carefully prepared populations of atoms whose quantum states are driven into coherent oscillations. Even the stars scattered throughout the universe shine because quantum states inside their dense cores guide the probability of nuclear reactions. Without the quantum state, none of these processes could be understood or predicted. A deeper insight emerged when scientists explored quantum systems exposed to their environment. Interactions with surrounding particles, radiation, or vibrations cause the delicate coherence of the quantum state to fade. This process, known as decoherence, provided a clear explanation for why classical behavior dominates the macroscopic world. When a quantum system interacts with countless particles in its environment, the interference patterns encoded in its amplitudes become scrambled. The system cannot maintain the fragile alignment needed for coherent superposition. As a result, it begins to behave like a classical object with well-defined properties. Decoherence does not rewrite the rules of quantum mechanics. It shows how classical behavior arises naturally from quantum laws when systems grow large and entangled with their surroundings. Even temperature plays a role in shaping the quantum state. At higher temperatures, particles move rapidly and interact constantly, disturbing the coherence needed for quantum effects to remain visible. But when matter is cooled to extremely low temperatures, the quantum state becomes stable enough to reveal exotic phenomena. Atoms can merge into collective states where their wave functions overlap and behave as one. Electrons in superconductors move without resistance because their quantum states pair together in a delicate harmony that survives only when environmental noise is minimized. These low-temperature experiments offer some of the clearest windows into the nature of the quantum state, and they confirm that coherence is not an abstract mathematical curiosity, but a real physical resource. Throughout this exploration, one truth became undeniable. The quantum state does not merely describe isolated particles. It becomes even more revealing when multiple systems interact. When two particles meet and exchange energy or influence one another, their quantum states join into a larger structure that reflects all the ways their possibilities can combine. This combined state does not treat the particles as separate entities with independent fates. Instead, it weaves their amplitudes together so that the outcome of one may depend on the outcome of the other, not through communication, but through shared structure. This phenomenon is not speculation. It is observed in laboratories around the world where trapped ions, photons, and superconducting circuits are prepared in joint states that display correlations far beyond anything classical physics could allow. The mathematics describing this combined structure relies on the tensor product space, a larger landscape built from the individual Hilbert spaces of each system. Within this space, there exist states that can be written as simple combinations of the separate states and states that cannot be separated at all. The first kind describes ordinary, uncorrelated systems. The second kind describes entangled systems, whose properties are linked even when the particles are separated by great distances. Entanglement does not replace superposition. It extends it. It shows that the possibilities of one system can become bound to the possibilities of another in ways that defy classical reasoning, but remain fully consistent with experimental evidence. This realization forms the bridge between the mathematical foundation of quantum mechanics and the deeper phenomena that define the theory. Superposition reveals how a single system can exist in multiple possible states at once. Entanglement reveals how multiple systems can share a joint state that cannot be broken into independent parts. Both arise from the same linear structure of quantum amplitudes, and both are essential for understanding the true nature of the quantum world. By the time the foundations of the quantum state had been fully established, physicists were prepared to explore these consequences more deeply. The stage was set for one of the most profound and experimentally confirmed phenomena in science. It would challenge classical intuitions, reshape modern technology, and transform our understanding of reality. It would show how the quantum state, once thought to describe only individual particles, could forge connections between systems that no classical theory could replicate. With this foundation laid, the path now turns toward the heart of quantum behavior. It turns toward the idea that a system can exist in many possible states at once, and that these possibilities can interfere to create patterns unseen in any classical world. It turns toward the phenomenon of superposition, the quiet yet astonishing principle that reveals the full power of quantum mechanics. Superposition is one of the most familiar yet most misunderstood features of quantum mechanics, and it emerges naturally once the structure of the quantum state is fully accepted. The idea is not that a particle splits into separate copies of itself or travels along different paths in a literal physical sense. It is that the state describing the particle contains many possible configurations at once, and these configurations combine through amplitudes that can reinforce or cancel one another. This concept, though subtle, is not speculation. It comes directly from experiments performed across more than a century of rigorous investigation. Every time a particle encounters an arrangement where more than one path or outcome is possible, its quantum state can become a blend of those possibilities, and the results measured later depend on how these possibilities interfere. The double-slit experiment remains the clearest and most striking example. When a stream of electrons is sent toward a barrier with two narrow openings, each electron appears as a single point when it strikes the screen behind the barrier. Yet after many electrons accumulate, the overall distribution forms a pattern of alternating bright and dark regions, a hallmark of interference. It would be reasonable to think that the electrons somehow pass through both openings at the same time, but the quantum description provides a more precise explanation. The electron's state becomes a combination of the state that corresponds to passing through the left opening and the state that corresponds to passing through the right opening. These two components of the state carry amplitudes that interfere with each other. Where the amplitudes align, the probability of finding the electron increases. Where the amplitudes oppose one another, the probability decreases. The resulting pattern is not caused by the physical electron splitting. It is caused by the structure of the quantum state, which holds more than one possibility until a measurement forces a definite outcome. Experiments with photons, neutrons, atoms, and even large molecules confirm the same principle. When single particles of any kind encounter an arrangement of paths or possibilities, their quantum states can form superpositions. This behavior persists across different systems and scales, always revealing itself through interference patterns that cannot be explained by classical statistics. The precision of these experiments leaves no room for alternative explanations. Even when particles are sent one by one, with long delays between them, the interference pattern still forms. This shows that the pattern does not arise from particles interacting with one another. It arises from the amplitudes encoded within each particle's state. Superposition also reveals itself in experiments that involve internal properties rather than spatial paths. Consider the Stern-Gerlach experiment, which measures the orientation of an electron's intrinsic angular momentum, or spin. When a beam of electrons passes through the magnetic field inside the apparatus, the electrons split into two distinct paths, corresponding to two allowed spin states. If the electrons are prepared in a definite spin state aligned with the measurement direction, they always follow the same path. But if they are prepared in a state oriented at a different angle, the quantum state becomes a superposition of the two possible spin orientations. When measured, each electron still chooses one of the two paths, but the relative frequencies of these outcomes reflect the amplitudes present in the superposition. This behavior is not an interpretation. It is observed directly in laboratories around the world. The distinction between a superposition and a classical mixture becomes clear when the differences in interference are examined. A classical mixture is a statistical combination of many particles, each with a definite but unknown state. A quantum superposition is a single system whose state contains multiple possibilities at once. Classical mixtures cannot produce interference patterns because they lack the delicate phase relationships that superpositions possess. Quantum superpositions can produce interference as long as their coherence is maintained. When this coherence is lost, usually because interactions with the environment disturb the phase relationships, the system transitions from a superposition to a mixture. This process is decoherence, and it represents one of the clearest demonstrations of the boundary between quantum and classical behavior. Decoherence has been measured in superconducting qubits, trapped ions, and atomic systems, confirming that superpositions are real physical states that require isolation to remain intact. Superposition also lies at the heart of quantum technologies. Superconducting qubits used in quantum computing are designed to hold superpositions of electrical current flowing clockwise and counterclockwise at the same time. Trapped ions are prepared in superpositions of spin states that can be manipulated with finely tuned laser pulses. Single photons are routinely placed into superpositions of polarization states for use in quantum communication protocols. These experiments are not conceptual demonstrations. They involve real devices operating under carefully controlled conditions, and they rely on superposition to function. As strange as superposition may seem, it becomes more intuitive when viewed as a consequence of linearity. The Schrödinger equation is linear, meaning that if two states are possible solutions, any combination of them is also a possible solution. This principle appears in many areas of physics. Musical notes combine to form chords. Water waves add together to form new patterns. But in quantum mechanics, the linearity applies to amplitudes that determine probabilities, making the effects far more profound. The interference patterns seen in experiments reflect this linearity directly. Superposition does not imply that reality splits into parallel versions. It simply reflects how amplitudes combine inside the quantum state. The lessons drawn from superposition reveal a world where particles are not confined to single configurations until they are measured. Instead, they explore multiple possibilities encoded in a single quantum state. These possibilities combine and evolve, guided by smooth mathematical rules, until measurement forces one of them to become a definite outcome. The measurement does not uncover a predetermined value. It converts the delicate balance of possibilities into a single result, following the probabilities encoded by the amplitudes. Yet even as superposition reveals the richness of individual quantum systems, it also hints at something deeper. When two or more systems interact, their superpositions can intertwine. The possibilities of one system can become linked with the possibilities of another. The combined state can contain correlations that cannot be broken down into separate parts. This phenomenon cannot be explained by superposition alone. It requires a new idea, one that extends the structure of the quantum state into a realm where information becomes shared across systems in ways no classical theory can match. With superposition fully understood, the path now leads naturally to the next phenomenon. It leads to the idea that two particles, once connected, can share a state so closely that the outcome of one becomes tied to the outcome of the other, even when great distances separate them. It leads to entanglement, the most celebrated and often misunderstood feature of quantum mechanics, a feature that pushes the limits of classical intuition, yet remains supported by some of the most precise experiments ever performed. The more scientists examined superposition, the more they realized that it was not merely a mathematical curiosity, but a universal principle woven into the behavior of every quantum system. It applied to electrons drifting through vacuum chambers, to atoms arranged in carefully controlled traps, to photons prepared in beams of pure light, and even to large molecules cooled and isolated from their environment. In each case, the quantum state could hold many possibilities at once, and these possibilities would reveal themselves through interference patterns whenever the system was allowed to evolve without disturbance. What changed from one experiment to another was not the principle itself, but the difficulty of maintaining coherence long enough for interference to appear. The larger the system, the more easily decoherence swept the superposition away, leaving behind a classical mixture that no longer carried the subtle phases needed for quantum behavior. This realization helped explain why everyday objects do not display superposition in any noticeable way. A grain of dust or a pebble on the ground interacts constantly with light, air molecules, and thermal vibrations. Each interaction leaks a tiny amount of information about its quantum state into the surrounding environment, disrupting the coherence between different possibilities. These disturbances accumulate rapidly, erasing interference before it can manifest on any visible scale. In contrast, particles that are isolated, cooled, or shielded can maintain coherence long enough for their superpositions to become visible through experiments that detect their interference. The difference is not that microscopic systems obey different laws. The difference is that microscopic systems can be protected from decoherence, while macroscopic systems cannot. This insight guided physicists toward new experimental techniques designed to preserve superposition for longer periods of time. In ultra-high vacuum chambers, collisions with stray particles are minimized. In dilution, refrigerators cooled to temperatures close to absolute zero. Thermal noise is reduced to nearly nothing. Superconducting circuits are designed with geometries that protect delicate currents from external disruptions. Laser cooling techniques trap atoms in orderly arrays, slowing their motion and improving their coherence times. These technologies do not create superposition. They reveal it, exposing the underlying quantum structure that is always present but often hidden beneath layers of environmental interaction. As scientists built these controlled environments, they began to explore superpositions in ways that went far beyond simple two-path experiments. They created superpositions of different energy states, different spin states, different directions of motion, and even different collective states involving many particles at once. In one remarkable class of experiments, researchers used superconducting circuits to create superpositions of electrical currents flowing in opposite directions. These macroscopic currents involved trillions of electrons, yet the system behaved as a single quantum object as long as it remained shielded from disturbance. This did not mean that trillions of electrons independently occupied trillions of states. It meant that the quantum state of the circuit as a whole contained more than one allowed configuration at once, a direct demonstration that superposition is not limited to tiny scales, but is a universal feature of nature. The same principles appeared in experiments with matter waves. When molecules composed of dozens or even hundreds of atoms were cooled, isolated, and sent through interferometers, they produced fringe patterns just like electrons and photons. The more complex the molecules became, the more challenging the experiment grew. Yet the results were clear. As long as coherence survived, superposition followed. This confirmed that quantum mechanics did not draw a strict boundary between small and large. It drew a boundary between coherent and decohered, between protected and disturbed. The classical world emerged not because quantum rules stopped working, but because maintaining coherence became overwhelmingly difficult as the number of particles increased. These findings strengthened the understanding that the wave-like behavior of quantum systems was not a metaphor. The amplitude describing a particle behaved mathematically like a wave, capable of spreading, overlapping, and interfering with itself. Yet it was not a physical wave made of matter or energy. It was a representation of the possibilities contained within the quantum state. When scientists measured the location of a particle, the result appeared as a single point, not a spread-out wave. This did not contradict the wave-based description. It highlighted the distinction between the structure of the state before measurement and the definite outcome produced by the measurement itself. The wave described the probabilities. The measurement revealed one result according to those probabilities. This interplay between the smooth evolution of superposition and the abrupt finality of measurement lay at the heart of quantum behavior. It explained how particles could explore many paths at once, yet still appear in one location when observed. It explained why interference patterns built up slowly over many trials, even though each particle left only a single dot on the detector. And it explained why the probability distribution of outcomes matched the structure of the underlying amplitudes with extraordinary accuracy, as confirmed in experiment after experiment. Superposition also illuminated the essential difference between knowing and disturbing in the quantum world. In classical physics, learning more about a system does not usually change the system itself. A thermometer measures temperature without altering it significantly. A camera captures an image without forcing the objects in view to change their shape. But in quantum mechanics, measurement is not passive. It is an interaction that reshapes the quantum state. When detectors are placed at the openings of a double-slit experiment, the interference pattern disappears. Not because the electron changes its mind, but because the act of measurement destroys the coherence between the two possible paths. The state collapses into one definite possibility, erasing the delicate interference that would have appeared otherwise. This fact is not a philosophical interpretation. It has been confirmed repeatedly through experiments with electrons, photons, atoms, and artificial quantum systems. As scientists expanded their understanding of superposition, they found that it naturally prepared the way for something even more remarkable. If a single system could hold many possibilities at once, then two systems brought together might share combinations of possibilities that no classical system could replicate. The superpositions belonging to each particle could intertwine, forming a joint structure that linked their outcomes in ways far beyond ordinary correlation. This joint structure did not require communication, influence, or unknown forces. It required only the mathematics of the quantum state and the linearity that allowed amplitudes to combine in complex ways. This revelation marked the transition from superposition to entanglement. It showed that the possibilities of one particle could become inseparably connected to the possibilities of another, creating relationships between distant systems that defied classical explanation. And just as superposition was revealed through interference patterns, entanglement would reveal itself through correlations that no classical theory could match. Correlations measured with exquisite precision in experiments that reshaped modern physics. As the understanding of superposition deepened, scientists began to realize that its consequences reached far beyond the striking demonstrations of interference. The principle was not limited to particles moving through space or to the orientation of spins. It applied to every measurable property of a quantum system. Energy levels, positions, momenta, internal states, collective motions, and even the behaviors of complex artificial systems could all exist in combinations of possibilities as long as coherence was preserved. The reach of superposition stretched across the entire quantum world, shaping how information was stored, how systems evolved, and how experiments unfolded. Because the principle was so universal, researchers found that superposition was not merely a trait of isolated particles, but a powerful resource that could be manipulated and controlled. In quantum computing, for example, the ability to place qubits into superpositions of 0 and 1 allowed algorithms to explore many computational pathways at the same time. This simultaneous exploration was not a mystical multiplication of worlds. It was a natural consequence of amplitude-based evolution. Quantum algorithms were crafted to guide the interference of amplitudes so that unwanted possibilities cancelled out while the desired outcomes reinforced one another. The advantage did not come from performing many computations at once. It came from steering a single quantum state through a landscape of possibilities in such a way that the final interference highlighted the correct answer. This perspective helped clarify one of the most common misconceptions about superposition. It did not imply that a system somehow occupied two literal states at the same time in a classical sense. Instead, It meant that the quantum state contained multiple allowed configurations, and the system evolved according to how these configurations interfered. When the system interacted with a measurement device, it produced a definite result, consistent with the probabilities encoded by its amplitudes. The intermediate possibilities existed only within the quantum state, and their physical impact appeared in the interference patterns, not in any observable duplication of the system itself. The importance of coherence in these processes could not be overstated. Without coherence, superpositions lost their ability to interfere, and the advantages they offered evaporated. This problem drove researchers to engineer increasingly sophisticated environments that protected quantum systems from external disturbance. Shielded cavities isolated photons for extended periods. Magnetic traps suspended ions in near-perfect vacuum. Superconducting materials were cooled to temperatures only a fraction of a degree above absolute zero. Each method shared a common goal: prevent the delicate quantum phases from being disturbed so that the superposition could evolve cleanly and predictably. To illustrate how fragile coherence can be, consider a single photon prepared in a superposition of different polarization states. If the photon travels through a pristine fiber in a tightly controlled environment, the superposition remains intact. The amplitudes for the two polarizations maintain their relative phase, allowing interference to occur later. But if the fiber contains imperfections that scatter the photon, or if vibrations disturb its path, the coherence between the two components fades. The photon still arrives at the detector, but the interference pattern disappears. What remains is a classical mixture of outcomes rather than a quantum superposition. The experiment has not broken the rules of quantum mechanics. It has revealed the central role that coherence plays in preserving quantum behavior. These insights reinforce the idea that superposition was a dynamic, evolving structure rather than a static condition. It flowed and shifted with time, responding to potentials, interactions, and disturbances. The future of the system depended on the delicate relationships among the amplitudes contained in its state. When these relationships remained intact, interference patterns revealed the presence of superposition. When they were destroyed by noise or uncontrolled interactions, the system behaved classically. This interplay between coherence and decoherence provided one of the clearest bridges between the quantum and classical worlds, showing how the familiar behavior of large objects emerged naturally from the deeper rules of quantum mechanics. The breadth of experiments exploring superposition continued to expand. Physicists created superpositions of atoms separated by distances many times their size. They generated superpositions of collective motions in mechanical resonators, where tiny structures vibrated in combinations of states normally associated only with light or electrons. They placed superconducting circuits into energy superpositions that oscillated with exquisite regularity. Every one of these experiments confirmed the predictions of quantum mechanics, showing that superposition was not confined to the realm of theory, but appeared whenever coherence was preserved. The more precisely researchers refined their techniques, the more striking the demonstrations became, pushing the boundary between quantum and classical behavior ever outward. Yet for all these achievements, superposition alone could not explain the most extraordinary feature of quantum mechanics. A single particle could hold many possibilities at once, but the full power of the quantum state appeared when multiple systems shared their possibilities in a joint structure. These shared structures produced correlations that no classical model could reproduce. Correlations that violated assumptions about locality and independent behavior that had been deeply embedded in classical thinking for centuries. These correlations did not require signals or messages. They arose from the way quantum amplitudes combined in the larger state of the system. The path from superposition to entanglement was therefore not a leap, but a natural step, built on the same principles that guided every aspect of quantum behavior. The transition began when scientists asked a simple but profound question. If a single particle can exist in more than one possible state, what happens when two particles interact? Do their combined possibilities simply sit side by side, untouched and unrelated? Or do the amplitudes describing one particle intertwine with the amplitudes describing the other in a deeper way? Experiments showed that the latter was true. When particles interact, their states merge into a single combined state that cannot always be separated into individual parts. This combined state carries correlations that persist even when the particles are separated. These correlations do not come from hidden forces. They come from the structure of the quantum state itself. This realization signaled the beginning of a conceptual transformation. Superposition revealed how nature builds individual quantum systems from possibilities. Entanglement would reveal how nature binds multiple systems together in ways far beyond classical expectation. The next step in the story of quantum mechanics leads directly into this phenomenon, a phenomenon that reshaped 20th century physics, inspired some of the most important experiments ever performed, and continues to guide the technologies of the 21st century. Entanglement entered the history of physics not as a bold new idea, but as an uncomfortable implication of the quantum state. It emerged quietly from the mathematics, revealing itself whenever two particles interacted in a way that allowed their amplitudes to intertwine. At first, it was treated as a curious side effect, a strange but harmless feature of an already counterintuitive theory. Yet as scientists examined it more closely, they realized that entanglement was not a minor detail. It was a central and unavoidable consequence of quantum mechanics, one that challenged the deepest assumptions of classical physics. This was not a matter of interpretation or philosophical speculation. It was a matter of experiment, of measurements repeated across decades, across continents, and across generations, each one confirming the same conclusion. Nature does not treat separated systems as independent when their quantum states have once been joined. The idea took its first dramatic step into the spotlight in the year 1935, when Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper that would ignite one of the most famous debates in science. Their argument was simple. If quantum mechanics was complete, then it described every property of a system at every moment. But when two particles interacted and then separated, quantum mechanics predicted that the measurement of one could instantaneously determine the outcome of the other, no matter how far apart they were. Einstein called this strange implication spooky action at a distance, not because he believed in it, but because he believed it revealed a flaw in the theory. He suspected that hidden variables must exist, unknown factors that carried fixed properties and prevented the universe from behaving in such an unsettling way. The EPR paper was a challenge, an invitation to examine whether quantum mechanics could be considered a complete description of reality. For nearly 30 years, the debate remained philosophical because no experiment could distinguish between quantum mechanics and hidden variable theories. But in 1964, John Bell discovered a way to test the issue directly. He showed that any theory relying on local hidden variables would obey a strict mathematical inequality. Quantum mechanics predicted that certain correlations between entangled particles would violate this inequality. The challenge was clear: measure the correlations and compare them. If nature respected Bell's inequality, then hidden variables would survive. If nature violated it, then the world was fundamentally quantum, with entanglement woven into its structure. The first experimental tests were carried out in the 1970s and 1980s by researchers, including John Clauser and Alain Aspect. Their results were unmistakable. Entangled particles produced correlations that violated Bell's inequality, exactly as quantum mechanics predicted. These early experiments were already convincing, but skeptical minds pointed out potential loopholes. Perhaps the detectors were inefficient. Perhaps the particles were not truly separated. Perhaps some hidden signal slipped between them. Over the next decades, physicists closed these loopholes one by one. They used faster detectors, greater distances, independent random number generators, and careful timing to prevent any possibility of concealed communication. The breakthrough came in the year 2015, when several research groups performed loophole-free tests of Bell's inequality. These experiments used entangled electrons in diamond defects, entangled ions in separate traps, and entangled photons distributed across hundreds of meters. The results left no room for doubt. Nature violated Bell's inequality in every case, proving that no local hidden variable theory could explain the outcomes. The correlations between entangled particles were real, measurable, and far stronger than any classical model could permit. They did not arise from faster-than-light communication. Relativity remained intact. They arose from the structure of the quantum state itself, which bound the possibilities of both particles into a single combined entity. Physicists continued to push the boundaries of entanglement with ever more ambitious experiments. They entangled photons separated by tens of kilometers across optical fibers. They entangled ions held in different laboratories. They used the Messier satellite to distribute entangled photons between ground stations separated by more than 1,000 kilometers. These demonstrations were not theoretical proposals. They were real experiments carried out with real particles, confirming that entanglement remained intact even when the particles were separated across enormous distances. The correlations persisted because entangled systems are not linked by signals. They are linked by the shared quantum state that describes them both. To understand this more deeply, consider how entanglement forms. When two particles interact, their individual quantum states merge into a single combined state that cannot be written as a simple product of separate parts. Instead, the possibilities belonging to one particle become intertwined with the possibilities belonging to the other. The combined state contains terms that describe joint outcomes, such as one particle being found in one state while the second is found in another. The amplitudes describing these outcomes evolve together, and when a measurement is performed on one particle, the quantum state collapses in a way that reflects the correlations embedded within it. The measurement does not send information to the other particle. It reveals the structure of the combined state that has existed since the interaction. These correlations are not limited to one type of system. Photons can be entangled in polarization. Electrons can be entangled in spin. Ions can be entangled in internal energy. States, superconducting qubits can be entangled through shared electromagnetic fields. In each case, the behavior follows the same mathematical rules and matches the predictions of quantum mechanics with precise accuracy. The universality of entanglement across different systems, platforms, and technologies is one of the strongest confirmations that it is a fundamental feature of nature, not a quirk of a specific experiment. Entanglement does not violate relativity because it does not allow messages to be sent faster than light. The outcomes of individual measurements remain random, and only by comparing results after the fact do the correlations become clear. Nothing about entanglement permits control over which outcome occurs. The structure of the quantum state determines how the outcomes align, but it does not provide a way to influence one result or the other. This fact has been verified through experiments that isolate entangled particles across vast distances, ensuring that no signal can pass between them during the measurement. The correlations remain even when the particles are separated by distances that forbid any conventional communication. The reality of entanglement carries profound implications for how scientists understand the universe. It shows that quantum systems cannot always be understood in isolation. Their properties can be shared, distributed, or intertwined in ways that defy classical intuition. A complete description must consider the combined state of the entire system, not just its individual parts. This idea reshapes the concept of locality and reveals that the boundaries separating objects are not as sharp as classical thinking suggests. In the quantum world, relationships between systems can be as fundamental as the systems themselves. As researchers explored entanglement more deeply, they uncovered new ways to harness it. Entangled states became tools for quantum communication, allowing secure information transfer across long distances. They became the backbone of quantum networks designed to share information between distant devices. They became essential components in quantum computing, where entanglement allows qubits to explore complex correlations that classical computers cannot replicate, and they became windows into the nature of reality itself, providing some of the most powerful evidence that the universe is governed by quantum laws. The journey from the early debates of Einstein and Bohr to the modern experiments that confirm entanglement has been one of the most dramatic transformations in science. It revealed a universe structured not by fixed properties, but by shared possibilities. It showed that the deepest features of nature are often hidden beneath layers of classical behavior and emerge only when systems are isolated, cooled, or controlled with extraordinary precision. And it confirmed that entanglement is not an optional feature of quantum mechanics. It is an inescapable consequence of the quantum state, one that reshapes every level of understanding from the behavior of microscopic particles to the foundations of modern technology. With the principles of entanglement established, the story now turns to one of the most fundamental questions in quantum physics. How do superposition and entanglement differ, and why are they so often confused? The next step in this journey requires separating these two concepts with clarity and precision, revealing why one applies to individual systems, while the other describes relationships between multiple systems. The more physicists investigated entanglement, the clearer it became that this phenomenon did not simply reflect unusual behavior at the microscopic level. It revealed a deeper structure that classical physics could not imitate. Classical systems can be correlated in many ways. Two coins flipped by the same person may accidentally land on the same side. Two planets orbiting a star may share motion determined by the same gravitational pull. But classical correlations depend on shared causes or mutual influences that exist within the ordinary flow of time. Entangled correlations are different. They arise not from causes or signals, but from the structure of the quantum state that binds systems together. These correlations persist even when the systems are separated so widely that no classical explanation can account for the alignment between their outcomes. To appreciate how remarkable this is, imagine two particles created in a way that produces opposite spins. In a classical world, each particle would carry its spin orientation with it, like a tiny arrow pointing up or down. If you measured one and found it pointing up, you would conclude that the other had been pointing down all along. That would be ordinary correlation. But in an entangled system, the two particles do not carry predefined spins. Instead, they share a combined state that contains a superposition of joint possibilities. When one particle is measured, the outcome is random, but the combined state ensures that the second outcome aligns perfectly with the first, according to the correlations encoded within the shared amplitudes. The measurement does not reveal a hidden property. It collapses the shared state, selecting one of the correlated possibilities. This behavior has been verified countless times and matches the predictions of quantum mechanics with extraordinary precision. These correlations do not permit any kind of control or communication. A measurement performed on one particle yields a random result, and nothing done to that particle can change the distribution of outcomes observed at the distant partner. Only when the results are compared later do the correlations become visible. This fact prevents any conflict with relativity, preserving the rule that no information can travel faster than light. The strangeness lies not in communication, but in the shared structure of the quantum state, which does not respect the classical boundaries between distant systems. The physics of entanglement also challenges the classical idea that the properties of a system belong solely to that system. In an entangled pair, the individual particles do not carry definite values for the properties being measured. Instead, the definite properties belong to the pair as a whole. The correlation is the physical object, not the individual values. This insight was revolutionary because it meant that the universe cannot always be described by assigning local attributes to separate parts. Instead, a complete description must include relationships that stretch across space without requiring any physical medium to carry them. The idea would have seemed impossible in classical physics, yet it is supported by some of the most precise experiments ever performed. This shift in understanding influenced every area of modern quantum science. In quantum communication, entangled particles are used to distribute cryptographic keys that cannot be intercepted without revealing the intrusion. In quantum networks, entanglement is the resource that allows information to be shared securely between distant nodes. In quantum metrology, entangled states amplify the sensitivity of measurements, allowing scientists to detect signals far too faint for classical instruments. In quantum computing, entanglement enables qubits to explore high-dimensional correlations that cannot be reproduced by classical computers, making certain tasks exponentially more efficient. Yet entanglement is not easy to maintain. Like superposition, it is fragile. Interactions with the environment disturb the carefully balanced amplitudes that define the correlations. When this happens, the entanglement decays and the system reverts to a classical mixture. This fragility is one of the greatest challenges in building large-scale quantum technologies. Engineers must isolate qubits, cool them to extremely low temperatures, and protect them from stray vibrations, electromagnetic noise, and even the faint jiggle of thermal energy. Without such protection, the entanglement dissolves in moments, leaving behind nothing more than ordinary correlations. The difficulty of preserving entanglement has driven researchers to develop increasingly sophisticated techniques. Quantum error correction uses additional qubits to detect and correct disturbances before they destroy the entangled state. Quantum repeaters use entanglement swapping to distribute correlations across long distances without allowing noise to accumulate. Advanced optical fibers and satellite links are designed to transmit entangled photons while minimizing losses. Each of these innovations reflects the same truth. Entanglement is a resource that must be cultivated and nurtured, not something that appears effortlessly in nature. Experiments have revealed that entanglement can take forms far more complex than simple pairs of particles. Systems can be entangled in networks, creating webs of correlations that span many nodes. Entire groups of atoms can be prepared in collective entangled states that enhance precision beyond classical limits. Even macroscopic systems can display entanglement when cooled and isolated enough, though such demonstrations require extraordinary care. These many body entangled states do not defy the rules of quantum mechanics. They arise naturally from the same mathematical structure, showing that entanglement is not restricted to pairs, but can extend across systems containing many particles. As scientists explored these more complex forms, they discovered that entanglement was not only a physical resource, but a conceptual one. It provided a new way to think about information, not as a property carried by individual particles, but as a pattern embedded within relationships. This perspective reshaped how physicists understood the flow of information in quantum systems. It also inspired entirely new fields such as quantum information theory and quantum computing, which built their foundations on the interplay between entanglement and superposition. All these developments reinforce the idea that entanglement was not an optional feature of quantum mechanics, but an essential one. It emerged naturally from the structure of the quantum state whenever systems interacted. It survived across long distances without violating any principles of relativity. It carried correlations that classical physics could not reproduce, and it opened doors to technologies that exceeded the capabilities of classical devices. Entanglement was not a paradox to be resolved. It was a feature of the universe waiting to be understood. By this point in the story, the conceptual foundation for entanglement was firmly established, and experiments had confirmed its existence beyond any doubt. The next step was to compare it directly with superposition, separating the two concepts with clarity and precision. Many misunderstandings arise from confusing these phenomena, yet they describe different aspects of the quantum world. Superposition concerns a single system and the many possibilities encoded in its state. Entanglement concerns multiple systems and the correlations encoded in their shared state. Understanding the distinction reveals why both are essential and why neither can replace the other. As the 20th century progressed into the 21st, the study of entanglement expanded from a theoretical curiosity into a central pillar of modern physics. What began as a challenge posed by Einstein evolved into one of the most experimentally grounded phenomena in science. Every new experiment strengthened the evidence. Every refinement closed another loophole, and every measurement confirmed that quantum mechanics described a world in which the deepest connections between systems were not carried through space, but encoded in the structure of their shared state. This understanding forced scientists to rethink long-held assumptions about separability, independence, and the boundaries between physical systems. One of the most striking lessons drawn from these experiments was that entanglement did not fade with distance. Once two particles shared a quantum state, separating them by meters, kilometers, or even hundreds of kilometers did not diminish the strength of their correlations. Photons sent through long optical fibers or beamed between stations via satellites still displayed the same perfect alignment of outcomes predicted by the theory. No classical force could explain such behavior without violating the speed limits set by relativity. Yet no signal traveled between the particles. The structure of the shared quantum state determined the outcomes, not any exchange of information. This was not speculation. It was demonstrated repeatedly with precise timing controls and independent random number generators, ensuring that no classical influence connected the measurement events. These experiments also revealed how essential the choice of measurement basis was to understanding entangled systems. Just as superposition depended on how the quantum state was expressed, entanglement depended on how the combined state of two or more systems was decomposed. A pair of particles might appear perfectly correlated when measured along one direction, but uncorrelated when measured along another. This dependence was not a sign of inconsistency. It was a direct reflection of the geometry of quantum states, which allowed correlations to appear differently depending on the basis of measurement. The flexibility and richness of this structure stood in stark contrast to classical correlations, which remained fixed once established. Physicists explored these relationships in a wide range of systems. In trapped ion experiments, carefully timed laser pulses entangled the internal states of ions separated by small distances. In superconducting circuits, microwave fields mediated interactions that generated entanglement between artificial atoms. In optical experiments, nonlinear crystals produced pairs of photons whose polarizations were perfectly correlated. In each case, the experimental signatures were unmistakable. When measured in the correct bases, the outcomes violated the inequalities that defined the limits of classical correlations. When the measurements were recorded and compared, the pattern always matched the predictions of quantum mechanics. As the evidence mounted, entanglement became more than a physical effect. It became a tool for understanding the deeper structure of quantum theory. The fact that entangled systems could not be described by assigning properties to their individual parts suggested that information in quantum mechanics was inherently relational. The meaning of a measurement outcome depended not only on the system being observed, but also on its connections to other systems. This insight influenced many areas of theoretical physics, from the study of many-body quantum systems to the investigation of black hole information and the geometry of spacetime. Although these areas extend beyond the scope of this documentary, they all rely on the same foundational fact. Entanglement is a fundamental aspect of reality, not an emergent phenomenon or a mathematical trick. The fragility of entanglement also highlighted the role of decoherence in shaping the boundary between quantum and classical behavior. Just as superposition disappeared when coherence was lost, entanglement vanished when the delicate relationships between amplitudes were disrupted. Experiments confirmed that interactions with the environment could rapidly destroy entanglement unless systems were isolated with extraordinary care. This requirement drove the development of new techniques in cryogenics, vacuum engineering, and electromagnetic shielding. Without these safeguards, the correlations that defined entanglement could not survive long enough to be observed. Yet with them, entanglement could endure surprisingly long distances and times, long enough to be used in practical applications such as quantum communication and networked quantum devices. The importance of entanglement extended even to the simplest systems, reminding physicists that the universe did not always function according to classical assumptions. When two particles shared an entangled state, measuring one particle instantaneously reshaped the description of the other within the combined quantum state. This update in knowledge did not imply any physical influence. It reflected the fact that the entire system had been described by a single joint state from the beginning. The measurement simply restricted the possible outcomes within that shared structure. This perspective resolved the apparent paradox of entanglement without violating relativity or introducing hidden influences. The universe remained consistent with both quantum mechanics and the speed limit of light, because the correlations arose from information already encoded in the joint state, not from any transmission of new information. By this stage, entanglement had become an accepted and essential part of physics. It was woven into the design of quantum computers, quantum sensors, and quantum communication systems. It had been tested in laboratories on every continent and confirmed with an astonishing level of precision. It influenced theoretical frameworks, guided new experiments, and reshaped the way scientists thought about information, measurement, and the nature of physical reality. The initial discomfort that Einstein expressed had transformed into a profound appreciation for the subtle and powerful structure that entanglement revealed. With the evidence firmly in place, the next chapter of the story arrives at a critical turning point. Superposition and entanglement are often spoken of in the same breath, yet they describe fundamentally different aspects of quantum behavior. Superposition concerns the possibilities within a single system. Entanglement concerns the relationships between multiple systems. Both arise from the same mathematical foundations, yet their meanings and implications diverge in important ways. Understanding the difference between them is essential for grasping the true nature of quantum mechanics. The time had come to place superposition and entanglement side by side, not as competing ideas, but as distinct features of the same quantum framework. For decades, these two concepts had been woven into conversations about the quantum world, often blurred together in explanations that left their differences unclear. Yet, the distinction between them is precise, experimentally verified, and essential for understanding how quantum systems behave. Superposition belongs to single systems. Entanglement belongs to multiple systems. Both rely on the structure of the quantum state, yet they describe entirely different kinds of possibilities. Recognizing this difference transforms scattered ideas into a coherent picture, revealing how nature organizes information on its smallest scales. Superposition describes how a single quantum system can occupy several allowed configurations at once. These configurations exist as amplitudes that combine and interfere, guiding the evolution of the system until a measurement forces a definite outcome. Every experiment involving interference, whether with electrons, photons, atoms, or artificial qubits, confirms the presence of superposition. The system does not split or duplicate. Instead, it holds a collection of possible outcomes encoded in its quantum state. The behavior revealed through interference patterns is a direct demonstration of how these possibilities interact. Entanglement, by contrast, describes how the quantum state of a combined system can contain correlations that cannot be separated into individual parts. When two particles become entangled, their joint state cannot be written as a simple product of separate states. Instead, the amplitudes describing each particle become woven together, encoding relationships that persist, even when the particles are separated by great distances. These correlations do not arise from communication or hidden signals. They arise from the structure of the combined state and have been confirmed by some of the most precise experiments ever performed. Bell tests, performed repeatedly with photons, ions, electrons, and superconducting qubits, show that entangled correlations violate the limits of classical physics. The mathematical foundation underlying both phenomena is the linearity of the quantum state. For a single system, linearity allows states to combine into superpositions. For multiple systems, the same linearity creates a tensor product space where entangled states naturally arise. This shared mathematical origin often leads to confusion, as both superposition and entanglement involve the combination of amplitudes. Yet the difference is clear. Superposition involves combinations of possibilities within one system. Entanglement involves combinations of possibilities shared between systems. Experiments reveal this distinction with elegant clarity. Consider a qubit in a superposition of 0 and 1. When measured, it produces a definite outcome, and the interference, patterns generated by repeated experiments, confirm the presence of superposition. Now consider two qubits prepared in an entangled state. Measuring one qubit does not reveal a pre-existing value. Instead, it determines the outcome of the other qubit according to the correlations encoded in their shared state. If the qubits were merely in individual superpositions, the correlations would not exceed classical limits. Only entanglement produces the strong correlations needed to violate Bell inequalities. Superposition and entanglement also differ in how they respond to noise and decoherence. A superposition can survive as long as its coherence remains intact. Entanglement requires coherence not only within each system, but also between them. This makes entanglement more fragile, demanding even greater isolation to preserve the joint state. Experiments with trapped ions, superconducting qubits, and optical photons reveal that superposition can often endure longer than entanglement under similar conditions. When the coherence between systems is lost, the entangled state collapses into a classical mixture, eliminating the non-classical correlations that define entanglement. Superposition within each system may remain, but the shared structure disappears. These differences extend naturally to practical applications. Quantum computing relies on superposition to explore many possible computational paths and on entanglement to link qubits in ways that allow complex algorithms to unfold. Superposition alone cannot generate the computational advantages that quantum computers promise. Entanglement alone cannot store information in the flexible manner needed for algorithmic evolution. Both are required. In quantum communication, entanglement distributes correlations across long distances with a level of security impossible for classical signals. Superposition contributes by enabling the encoding of quantum information in different bases, yet without entanglement, many communication protocols would fail. The two phenomena are complementary, each providing capabilities that the other cannot. The distinction becomes especially clear when considering how classical and quantum systems differ. Classical systems can form mixtures, but they cannot form superpositions because classical probabilities do not interfere. Classical systems can share correlations, but they cannot form entangled states because their combined behavior can always be explained by assigning properties to each part. Quantum systems, by contrast, can form superpositions because their amplitudes interfere, and they can form entangled states because their joint amplitudes create correlations that defy classical decomposition. These features are uniquely quantum and are responsible for the differences between the quantum and classical worlds. The use of density matrices highlights this distinction with mathematical precision. A single qubit in a superposition has a density matrix with off-diagonal terms representing coherence. A pair of qubits in a separable mixed state lacks these off-diagonal terms across the combined system, but an entangled pair displays off-diagonal terms that couple the states of the two qubits, revealing the presence of non-classical correlations. This difference can be detected through quantum state tomography, a technique that reconstructs the full density matrix of a system based on repeated measurements. These reconstructions leave no doubt. The structure of entangled states cannot be written as mixtures of product states. Their correlations cannot be explained by any classical model. Their signature is unmistakable. Examples from quantum optics provide some of the clearest demonstrations. In superposition experiments, a single photon may exist in a blend of horizontal and vertical polarization. Interference patterns confirm the presence of this superposition. In entanglement experiments, two photons may be prepared so that their polarizations are always opposite or always aligned, depending on the measurement basis. A measurement on one photon instantly determines the outcome of the other within the shared state. Across hundreds of kilometers, these correlations remain intact. They do not require communication. They do not violate relativity. They reveal the underlying relationship between the two photons encoded in their joint state. The clarity of the distinction becomes greater the more deeply it is examined. Superposition explores the space of possibilities within a single system. Entanglement explores the relationships between different systems. Superposition is revealed through interference patterns. Entanglement is revealed through violations of classical inequalities. Superposition guides individual behavior. Entanglement guides collective behavior. Each phenomenon offers insights into different layers of quantum reality. With these features understood, the next steps in the story turn toward the tools scientists use to measure and confirm each phenomenon. Superposition reveals itself through interference. Entanglement reveals itself through correlations. The experiments used to detect these features form the backbone of modern quantum science, allowing researchers to verify that the strange predictions of quantum mechanics match the behavior of real particles. These tools also form the foundation of the technologies that will define the future of computation, communication, and measurement. Understanding the difference between superposition and entanglement requires not only examining their mathematical forms, but also seeing how experiments reveal them. The laboratory is where abstractions meet reality. It is where equations either survive scrutiny or crumble beneath the weight of observation. In the case of quantum mechanics, the experiments do not merely support the theory. They illuminate its structure, showing precisely how superposition emerges in isolated systems and how entanglement appears in composite ones. The distinction becomes unmistakable the moment one examines how each phenomenon is detected, measured, and confirmed with real particles. Superposition reveals itself through interference. When a single particle encounters a setup where more than one path is possible, its quantum state becomes a combination of those paths. The presence of superposition is confirmed when the outcomes show patterns that cannot be formed by classical mixtures. A classical mixture of paths produces a simple sum of probabilities. A quantum superposition produces fringes, oscillations, and cancellations that arise from the phases encoded in the amplitudes. This fact is clearest in the double-slit experiment, but appears in countless variations. Mach-Zehnder interferometers, Ramsey interference in atomic systems, and Rabi oscillations in superconducting qubits all reveal the same behavior. The structure of the interference pattern is a fingerprint of superposition, an unmistakable sign that the system contains more than one possibility at once. Entanglement reveals itself through correlations. When two systems share a joint quantum state, their measurement outcomes cannot always be described by assigning values to each system independently. Instead, the outcomes exhibit relationships that violate the inequalities satisfied by all classical models. Bell tests, performed repeatedly with different particles and in different conditions, reveal these correlations with extraordinary clarity. When experimenters choose measurement settings independently and at random, the correlations still appear. When the particles are separated by distances that prohibit any classical signal from reaching them in time, the correlations still appear. When detection efficiencies are increased to close loopholes, the correlations still appear. The consistency of these results across many decades and many platforms confirms that entanglement is not a classical correlation in disguise. It is a feature of the quantum state, emerging naturally from the tensor product structure that links the systems. The difference becomes even clearer when examining how superposition and entanglement behave under decoherence. A superposition exists as long as the system maintains coherence among its internal possibilities. If environmental noise disturbs the phase relationships, the superposition collapses into a classical mixture. Entanglement requires coherence not only within each system, but also between them. Noise can sever the delicate links that define the shared state, causing the entanglement to vanish even if each system individually retains some internal coherence. This distinction has been observed directly in experiments. Entanglement decays when the shared phase information is lost, and the resulting behavior becomes indistinguishable from that of a classical mixture. Superposition may survive longer, but the non-classical correlations disappear quickly unless extraordinary isolation and protection are maintained. These differences flow naturally into the techniques used to reconstruct quantum states. Quantum state tomography is a method that allows researchers to rebuild the density matrix of a system by performing a wide range of measurements. When applied to a system in superposition, tomography reveals off-diagonal elements in the density matrix corresponding to the coherence between different internal states. When applied to entangled systems, tomography reveals off-diagonal elements that link the states of the two systems. The presence or absence of these elements distinguishes superposition from mere mixtures and entanglement from merely correlated pairs. These reconstructions leave no ambiguity. The structure of the quantum state matches the theory exactly, showing that the differences between superposition and entanglement arise not from interpretation, but from measurable physical reality. The contrast also appears when scientists examine the mathematical objects used to describe multi-system states. A separable state is one that can be written as a combination of product states. A classical mixture of product states behaves predictably and complies with all the constraints of classical correlation. But an entangled state cannot be written this way. It contains terms that couple the systems in ways that cannot be decomposed. These states occupy regions of the tensor product space, inaccessible to classical models. They exist only because the amplitudes of the two systems have merged into a structure that binds their outcomes. The presence of such states is not assumed. It is measured. It appears in the density matrix. It appears in correlation experiments. It appears in violations of classical inequalities. It appears whenever two or more systems share a quantum state. The practical consequences of these differences are profound. Quantum computers rely on superposition to allow qubits to explore many possible configurations during computation. But without entanglement, the interference patterns that guide the system toward the correct answer cannot be sculpted effectively. Superposition provides the raw material, the landscape of possibilities. Entanglement provides the interconnected structure needed to shape the evolution of the system. In quantum communication, superposition allows information to be encoded in different bases, but entanglement allows information to be shared across distance with security and precision unattainable by classical means. In quantum sensing, entangled states allow measurement sensitivities that exceed classical limits, enabling the detection of faint signals that would otherwise go unnoticed. These applications highlight why the distinction matters. Superposition describes individual behavior. Entanglement describes collective behavior. Superposition reveals itself through interference patterns. Entanglement reveals itself through correlations. Superposition is protected by maintaining coherence within a single system. Entanglement requires coherence across multiple systems. These differences are not philosophical, they are operational. They determine how experiments must be designed, how devices must be built, and how information must be processed. As the understanding of these distinctions deepens, it becomes clear that superposition and entanglement are not separate islands, but interconnected features of a single landscape. Superposition allows each system to hold multiple possibilities. Entanglement allows systems to share these possibilities. Superposition is the foundation. Entanglement is the structure built upon it. Together, they form the two pillars of quantum mechanics, supporting the technologies that are now emerging from laboratories around the world. With these ideas firmly established, the next chapter turns toward the methods used to detect and measure both superposition and entanglement with precision. These methods form the bridge between theory and experiment, revealing how quantum behavior becomes visible in the data collected by real detectors under real conditions. The full comparison between superposition and entanglement becomes even more compelling when examined through the lens of real laboratory practices. The precision with which physicists can now manipulate quantum systems has transformed these once abstract concepts into tangible tools. Every modern quantum experiment, whether involving photons, ions, electrons, or superconducting circuits, demonstrates the distinction between these two phenomena with clarity that leaves no room for ambiguity. Superposition, at its core, is revealed whenever a single quantum system shows behavior that depends on the phase relationships between its possible states. These phase relationships determine how likely different outcomes are and how the interference pattern will appear. When researchers control the relative phase between the components of a superposition, they can steer the probabilities of measurement outcomes with remarkable precision. This control has become routine in countless platforms. Laser pulses adjust the phases of atomic superpositions. Microwave fields shape the states of superconducting qubits. Carefully timed magnetic fields prepare spins in coherent blends of orientations. Each of these techniques confirms that superposition is not an imagined feature of quantum mechanics. It is a physical property encoded in the quantum state and revealed through careful manipulation. Entanglement demands a different set of techniques because it involves multiple systems and the relationships between them. Instead of adjusting the phase within a single system, experimenters must create interactions that join the quantum states of two or more systems into a shared structure. In trapped ion laboratories, this is accomplished through laser-induced forces that couple the motion of one ion to another. In optical experiments, nonlinear crystals emit pairs of photons whose polarizations are linked. In superconducting circuits, microwave photons mediate interactions between qubits, creating correlations that cannot be broken down into separate parts. These processes do not merely produce aligned outcomes. They produce joint states with amplitudes that can only be described in the larger space formed by combining the individual systems. When experimenters probe these entangled states, they discover signatures that cannot arise from superposition alone. The measurements reveal correlations that cannot be explained by assigning any fixed properties to each particle before measurement. Instead, the outcomes must be determined by the shared structure of the joint state. The violation of Bell inequalities is the most famous example, but it is not the only one. Entanglement witnesses, measures derived from quantum information theory, and full-state tomography all provide independent confirmation. These measurements use different techniques, probe different aspects of the state, and rely on different statistical analyses. Yet they all converge on the same conclusion. The structure of entangled states exists beyond the reach of classical models. The different requirements for maintaining these states also illuminate the distinction. A superposition collapses into a classical mixture when environmental noise destroys the coherence between its components. Entanglement collapses when noise destroys the coherence shared between systems. This difference becomes vital in quantum technologies. A quantum computer cannot function without the ability to maintain superpositions within each qubit and entanglement between qubits. A quantum communication network cannot operate without preserving the shared correlations across distance. A quantum sensor cannot reach its ultimate sensitivity without entangling many particles into a collective state. The practical challenges reflect the theoretical distinction. Even the processes that create these states show how fundamentally different they are. A superposition can be produced by allowing a particle to encounter a situation with more than one path. A beam splitter splits the amplitude of a photon. A magnetic field splits the amplitude of a spin. A potential well shapes the amplitude of an electron. These are simple, direct manipulations of a single quantum system. Entanglement, on the other hand, requires coupling. Two systems must interact in such a way that their amplitudes merge into combinations that cannot be separated. This coupling is essential because it creates shared possibilities that no isolated system can develop on its own. All these observations lead to a conclusion that is both precise and profound. Superposition and entanglement are not two versions of the same idea. They arise from similar mathematical principles, but they describe different layers of quantum structure. Superposition describes how a single quantum state holds multiple possibilities. Entanglement describes how multiple quantum states merge into a shared structure of correlations. The difference is not philosophical or interpretive. It is operational, measurable, and grounded in evidence collected from decades of carefully controlled experiments. Recognizing this distinction allows scientists to design experiments with confidence, build technologies that exploit quantum behavior, and develop theories that capture the full richness of the quantum world. It brings clarity to the foundations of quantum mechanics and reveals how nature organizes information in ways that defy classical intuition, but remain entirely consistent with experimental observation. With this understanding firmly established, the next chapter turns to the experimental methods that allow scientists to detect, verify, and control both superposition and entanglement. These methods form the practical backbone of modern quantum science, bridging the gap between theory and the real world by revealing how quantum behavior becomes visible through the signals collected by precise instruments. The deeper physicists ventured into the quantum world, the more they faced a surprising challenge. Quantum behavior is real, measurable, and predictive, yet it often hides behind the veil of probability. The most important features of quantum mechanics, such as superposition and entanglement, cannot be touched or seen directly. They leave no marks on a detector unless the experiment is arranged with extraordinary care. The task became clear. If quantum mechanics described reality through amplitudes and possibilities, the only way to understand that reality was to design experiments that transformed those possibilities into patterns and correlations visible in measurement data. The experimental techniques that emerge from this challenge reveal not only how scientists detect quantum behavior, but also how the deepest structures of the theory manifest in the laboratory. Superposition reveals itself through interference patterns, a fact discovered long before quantum mechanics was formulated. When electrons or photons are allowed to traverse more than one possible path, the resulting probabilities show oscillations that cannot arise from any classical mixture. The apparatus does not need to be exotic. A simple double-slit arrangement, refined with modern detectors, displays the same unmistakable pattern. Each electron appears on the screen as a single dot, but as many electrons accumulate, their distribution forms alternating regions of high and low intensity. The pattern reflects the relative phases of the amplitudes associated with each path. When physicists adjust the geometry of the apparatus or add phase-shifting elements, the pattern shifts accordingly. Nothing in classical physics can produce these oscillations from single particle events. The fringes are the signature of superposition, the visible imprint of the amplitude-based structure of the quantum state. More sophisticated setups amplify this signature with remarkable precision. Mach-Zehnder interferometers split the amplitude of a photon into two paths and recombine them with adjustable phase differences. Ramsey interference experiments manipulate atomic superpositions with pairs of laser pulses, revealing coherence through oscillations in the measurement outcomes. Superconducting qubits undergo Rabi oscillations, where the probability of finding the system in one state or another cycles rhythmically in time. Each of these techniques transforms the invisible phases within the quantum state into measurable signals. The oscillations appear only when a true superposition exists. If decoherence destroys the delicate phase relationships, the oscillations fade, and the system behaves like a classical mixture. These methods provide some of the most direct evidence for the presence or absence of superposition in a controlled environment. Entanglement requires an entirely different set of techniques because its presence cannot be detected by examining either system individually. Instead, experimenters must measure correlations between systems and compare them to the limits of classical physics. Bell tests remain the most famous example. In these experiments, scientists prepare two particles in an entangled state and send them to separate locations where independent measurements are performed. The measurement settings are chosen randomly and independently to ensure no hidden influence can determine the outcomes in advance. When the results are collected and compared, the correlations are found to violate the inequalities that bind all classical models. These violations are not small, they are significant, repeatable, and consistent across platforms. Experiments with photons, ions, electrons, and superconducting qubits all yield the same result. Entanglement produces stronger correlations than any classical theory can allow. The precision demanded by such experiments has led to extraordinary engineering. Detectors must be fast enough to register outcomes within time windows that exclude the possibility of communication between the systems. Measurement settings must be chosen quickly and unpredictably to prevent any hidden coordination. The particles must be separated far enough that no light speed signal can pass between them before the measurements occur. All these conditions have been met repeatedly, closing loophole after loophole. The result is a body of evidence confirming that entanglement is real and that its correlations arise from the quantum state itself, not from any hidden mechanism. Beyond Bell tests, other methods provide complementary evidence. Entanglement witnesses are designed to detect non-classical correlations without reconstructing the entire quantum state. They rely on inequalities derived from quantum information theory to identify states that cannot be written as separable mixtures. Quantum state tomography provides a more complete picture, allowing scientists to reconstruct the full density matrix of a composite system through a series of measurements. These reconstructions reveal off-diagonal terms that couple the states of the two systems, confirming the presence of entanglement. Tomography has been performed on entangled photons, ions, and superconducting qubits, each time revealing structures that match the predictions of quantum mechanics. Maintaining entanglement and superposition requires isolation from the environment. Even tiny interactions with air molecules, thermal vibrations, or stray electromagnetic fields can destroy coherence and collapse these states into classical mixtures. To preserve quantum behavior, experiments operate in extreme conditions. Trapped ions float in vacuum chambers, where collisions with stray atoms are almost non-existent. Superconducting circuits are cooled inside dilution refrigerators to temperatures only a tiny fraction of a degree above absolute zero. Optical fibers used to transmit entangled photons are shielded from vibrations and impurities that could disturb the delicate correlations. These techniques do not create quantum behavior. They protect the quantum behavior that already exists from the noise of the surrounding world. Another method used to detect quantum features is quantum non-demolition measurement, which allows certain properties of a system to be observed without destroying the coherence needed for further evolution. These measurements provide a window into the dynamics of quantum systems that would otherwise be hidden behind the collapse induced by traditional detection. They have allowed scientists to monitor the evolution of superpositions and entanglement over time, verifying that these states persist as long as environmental noise is minimized. Modern quantum technologies rely heavily on these detection methods. Quantum communication channels use entanglement verification to ensure that transmitted information remains secure. Quantum computers use tomography to calibrate multi-qubit gates and verify that entanglement is produced correctly. Quantum sensors use interference patterns to detect tiny changes in physical quantities such as magnetic fields, gravitational gradients, or time intervals. These applications are not futuristic or hypothetical. They operate in laboratories and prototype devices today, grounded entirely in experimentally confirmed quantum phenomena. The success of these techniques underscores a central truth about quantum mechanics. Its predictions are not vague or interpretive. They are precise, operational, and measurable. When the structure of the quantum state contains superposition, interference reveals it. When the structure contains entanglement, correlations reveal it. These experiments form the bridge between mathematical theory and physical reality, showing that the most subtle features of quantum mechanics leave unmistakable signatures in the world of measurement. With these tools in hand, scientists have unlocked new ways to manipulate matter and information at the smallest scales. The next chapter follows the path of superposition into the heart of quantum computation, showing how the delicate balance of amplitudes becomes a resource for solving problems that lie far beyond the reach of classical computers. The growing mastery of experimental techniques allowed physicists to move beyond merely observing quantum behavior and toward controlling it with increasing precision. The ability to prepare, manipulate, and measure superpositions and entangled states opened a new frontier, one where the boundary between theoretical prediction and laboratory implementation became thinner with each decade. Scientists no longer had to infer the structure of quantum states from indirect signatures. They could sculpt those states deliberately, shaping their evolution in ways that exposed the inner workings of quantum mechanics with clarity that previous generations could hardly imagine. One of the central methods for revealing superposition is the controlled manipulation of phases. In the language of quantum mechanics, the relative phase between components of a superposition governs how those components interfere. If the phases align, the interference strengthens certain outcomes. If the phases oppose one another, the interference cancels them. This delicate balance forms the backbone of interferometry. In a Mach-Zehnder interferometer, for example, a photon is split into two amplitude paths that later recombine. By adjusting the length of one path or introducing a transparent material that slows the photon, experimenters change the relative phase between the two paths. The resulting interference pattern shifts predictably. This shifting provides a direct measurement of the coherence of the superposition. When coherence is intact, the fringes remain sharp and well-defined. When noise disrupts the phase relationship, the fringes blur and vanish. Similar techniques appear in experiments using atoms and superconducting qubits. In Ramsey interference, atoms are placed into superpositions of internal energy states using a sequence of laser pulses. The phases of these states evolve at different rates, creating oscillations in the probability of each outcome. By counting how many atoms end up in each state, researchers observe the interference pattern. The frequency and visibility of these oscillations provide precise information about the coherence of the system. In superconducting circuits, a controlled electromagnetic field drives transitions between energy levels, creating oscillations that map the evolution of a superposition in real time. The clarity of these oscillations is a direct measure of how well the system is isolated from environmental noise. These methods highlight a key fact about superposition. It is not enough to prepare multiple possibilities. The relationship between those possibilities must be preserved. Without coherence, the amplitudes cannot interfere, and the system behaves classically. The persistence of interference patterns serves as a direct indicator of how successfully a quantum system maintains coherence. In laboratories around the world, these patterns guide the design of devices, the refinement of cooling systems, and the engineering of shielding techniques. The quest to maintain coherence is, in many ways, the quest to harness the full power of quantum mechanics. Entanglement requires an even more delicate balance. Because entangled states involve correlations between systems, they demand precise control not only of each individual system, but also of the interactions that join them. These interactions must be engineered so that the amplitudes of the combined system merge into a structure that cannot be written as separate parts. In trapped ion experiments, this is achieved by coupling the motion of two ions through carefully tuned laser fields. The motion acts as a shared resource that links the states of the ions. When the interaction concludes, the ions emerge with their internal states entangled. Experiments confirm this by examining the correlations in their measured outcomes, which exceed the limits of classical physics. In superconducting qubit systems, entanglement is created through microwave pulses that mediate interactions between the qubits. These pulses are shaped in time to produce the desired joint evolution. The resulting entangled states can then be measured or used as the building blocks of quantum algorithms. Optical experiments use nonlinear crystals to produce pairs of entangled photons, whose polarizations share a quantum state. By directing each photon to a different detector, and choosing measurement bases independently, scientists confirm the presence of entanglement through the correlations in their outcomes. As with superposition, decoherence threatens the stability of entangled states. The moment noise disrupts the shared coherence between systems, the entanglement decays. This decay is visible in the measurement statistics. Correlations that once violated classical inequalities begin to shrink until they no longer exceed classical limits. The transition from entangled to separable is not philosophical, it is measurable. It reflects the sensitivity of entangled states to disturbance and the importance of isolation in experiments involving multiple systems. The precision required to detect and preserve entanglement led to the development of quantum state tomography. By performing many measurements in different bases, scientists reconstruct the full density matrix of a composite system. The density matrix reveals not only the probabilities of different outcomes, but also the coherence between systems. When the off-diagonal elements linking the states of the two systems are substantial, the system is entangled. When those elements fade due to decoherence, the system becomes separable. Tomography provides a complete and quantitative picture, confirming the predictions of quantum mechanics to a remarkable degree. State tomography played a crucial role in the first demonstrations of entanglement in superconducting qubits, in trapped ions, and in photonic circuits. It continues to be a vital tool for calibrating quantum processors, verifying quantum communication channels, and diagnosing sources of noise in cutting-edge devices. These reconstructions bridge the gap between abstract mathematical structures and the physical systems that embody them, making the distinction between superposition and entanglement visible in measured data. The detection of these states is not limited to laboratory systems. Experiments using atomic ensembles and solid-state defects reveal entanglement in systems containing thousands of particles. Although the structure becomes more complex, the same principles apply. Coherence preserved within the ensemble creates collective behavior that can be measured through fluctuations and correlations. These demonstrations show that entanglement is not confined to isolated pairs of particles. It can extend across entire groups when the conditions are right, allowing scientists to probe quantum behavior in increasingly large and complex systems. As experimental control improved, researchers developed entanglement witnesses that provide simpler tests for identifying entanglement without reconstructing the full state. These witnesses rely on inequalities derived from the mathematics of quantum information. When the measured values violate these inequalities, the presence of entanglement is guaranteed. Witnesses provide a practical way to verify entanglement in high-dimensional systems where tomography would require too many measurements. Through all these methods, the experimental evidence remains consistent. Superposition reveals itself through interference. Entanglement reveals itself through correlations. Both require coherence. Both vanish when noise dominates. And both are essential for the technologies that have begun emerging from quantum research laboratories. The next step in the story turns toward the techniques used to maintain coherence long enough for these effects to be useful in real applications. Quantum systems must be cooled, isolated, and protected. Error correction must be implemented. Strategies must be devised to counteract the disruptive effects of the environment. The final part of this chapter will explore these challenges and show how scientists push the limits of what can be measured and preserved. As experiments grew more ambitious, scientists found themselves confronting a fundamental obstacle. Quantum systems are extraordinarily sensitive. The same delicacy that allows them to exhibit superposition and entanglement also makes them vulnerable to the slightest disturbance. Every interaction with the environment, every stray vibration, every flicker of thermal energy threatens the coherence needed to maintain quantum behavior. For quantum mechanics to be observed, measured, and ultimately used as a tool, researchers had to learn how to protect quantum states from the world around them, often with engineering approaches as creative as they were precise. One of the most effective methods for preserving coherence is cooling. At high temperatures, particles in any material vibrate constantly. bumping into one another and exchanging energy. These collisions disrupt the phases that define a quantum superposition, or the correlations that define an entangled state. By cooling a system to temperatures near absolute zero, scientists reduce thermal motion to a level where disturbances become rare. Dilution refrigerators, intricate machines that use mixtures of helium isotopes to reach temperatures only a tiny fraction of a degree above absolute zero, are now standard tools in laboratories studying superconducting qubits. At these temperatures, the coherence times of quantum states stretch long enough for interference patterns to be recorded and entangled states to be created with high fidelity. Vacuum plays an equally important role. Air molecules are constantly moving and colliding. Even a single collision between an air molecule and an isolated quantum system can destroy coherence. To prevent this, experiments involving trapped ions, ultra-cold atoms, and matter wave interferometers are conducted inside vacuum chambers, where the number of stray atoms is reduced to an incredibly low level. Inside these chambers, ions float almost freely, held in place by electromagnetic fields rather than physical barriers. Without stray collisions, their quantum states remain coherent for long enough to carry out complex manipulations. The purity of the vacuum ensures that the delicate amplitude relationships inside the quantum state remain undisturbed. Shielding also protects quantum systems from external electromagnetic fields. Even faint fluctuations in ambient fields can modify the phases of quantum states in unpredictable ways. To counter this, superconducting qubit systems are enclosed within layers of metal and magnetic shielding that prevent stray fields from entering. Optical experiments use stabilization techniques to keep laser frequencies and path lengths fixed with astonishing precision. Mechanical interferometers are mounted on vibration isolation platforms that dampen tiny tremors from the environment. Each layer of shielding, cooling, and isolation is part of a strategy aimed at a single goal: preserve coherence long enough to reveal and manipulate the underlying quantum behavior. Yet even with these precautions, decoherence can never be fully eliminated. The environment finds its way in through channels that cannot be completely sealed. To overcome this limitation, scientists developed quantum error correction, a method that uses redundancy and entanglement to protect quantum information. In classical systems, error correction is straightforward. Bits can be copied and compared, but quantum states cannot be copied due to the no-cloning theorem. Instead, quantum error correction encodes information across multiple qubits in such a way that errors affecting one qubit can be detected by examining correlations with the others. These correlations reveal whether a disturbance has occurred without measuring or collapsing the protected information itself. Experimental progress in this area has been remarkable. Researchers have demonstrated the ability to detect and correct certain errors in small quantum processors, preserving coherence for longer than would otherwise be possible. Another strategy for maintaining coherence is dynamical decoupling. This technique uses sequences of precisely timed pulses to cancel out the effects of environmental noise. Just as a spinning top resists the influence of small disturbances, a quantum system subjected to carefully chosen pulses can resist decoherence by averaging out unwanted interactions. These pulse sequences require exquisite timing, but have proven effective in systems ranging from trapped ions to electron spins in solid-state materials. They represent another example of how experimental ingenuity can extend the lifetime of quantum behavior. Quantum state verification plays an important role in ensuring that these protective measures are working. Scientists use tomography, interference, and correlation measurements to monitor how coherence decays over time. By observing the rate at which interference fringes lose visibility or measuring how entangled correlations weaken, they identify which sources of noise remain dominant. These measurements guide improvements in experimental design, helping researchers isolate systems more effectively, cool them more uniformly, and shield them more completely. The success of these techniques allows experiments to reveal quantum behavior with a clarity that earlier generations of scientists could scarcely imagine. superpositions lasting long enough for intricate interference experiments, entangled states surviving long enough to transmit correlations across kilometers, coherence preserved long enough to implement small quantum algorithms. These achievements confirm that the quantum world is not restricted to theoretical constructs. It lives in the laboratory, visible whenever noise is subdued and interactions are controlled. As scientists continue to refine their methods, new possibilities emerge. Larger entangled states become feasible. Longer coherent times become achievable. More complex quantum systems become accessible. The experimental frontier pushes outward, carrying the promise of technologies built on the delicate structure of the quantum state. With the ability to measure and preserve quantum behavior now firmly established, the path leads naturally to the next chapter of this story. Superposition does not merely reveal the structure of quantum systems. When harnessed with precision and control, it becomes a powerful resource. In the next chapter, the narrative turns toward quantum computing, where the coherent exploration of many possible states becomes a tool for processing information in ways that classical devices cannot match. Quantum computing is not merely an incremental improvement over classical computing. It is a revolution. At its core lies the ability to leverage the unique properties of quantum mechanics to perform calculations that were once thought impossible. The key to this power lies in the quantum bit, or qubit, which, unlike its classical counterpart, can exist not just in a state of 0 or 1, but in a superposition of both. This means a quantum computer can explore many possibilities simultaneously, offering exponential speedups for certain types of problems. Superposition, in essence, allows a quantum computer to represent a vast number of possibilities all at once. But superposition alone is not enough to achieve the true power of quantum computing. The real magic happens when multiple qubits interact with each other, and the entanglement between them allows quantum algorithms to reach outcomes far faster than classical ones. Entanglement creates a level of interdependence between qubits, allowing them to influence each other in ways classical bits never could. A quantum computer, powered by superposition and entanglement, can solve problems like factoring large numbers or searching large databases exponentially faster than any classical computer can manage. This dual power of superposition and entanglement allows quantum computers to excel at tasks that would take classical computers millennia to complete. For example, Shor's algorithm, when run on a sufficiently powerful quantum computer, promises to break the encryption schemes that underpin the security of the internet. But the full potential of quantum computing is not yet realized. The challenges of error correction, coherence time, and scaling quantum systems are immense. Each qubit is susceptible to interference from its environment, which can easily destroy the delicate superpositions that give quantum computers their power. Despite these challenges, progress is accelerating. Researchers are developing increasingly sophisticated qubits and error correction techniques, bringing us closer to a time when quantum computers will be able to outperform classical computers in more and more tasks. As quantum computing continues to advance, it will not replace classical computing. Instead, it will complement it. Classical computers will continue to excel at tasks that are straightforward, like browsing the web or running standard software applications. But for tasks involving large-scale simulations, complex optimization, or problems that involve enormous amounts of data, quantum computers will open doors previously unimaginable. Quantum communication takes the ideas behind quantum computing one step further, transforming the way we think about transmitting information. At its heart, quantum communication uses the strange but experimentally confirmed properties of quantum entanglement to create a new kind of security for the exchange of information. Unlike classical communication, where messages are sent from one place to another, quantum communication relies on shared entanglement between distant parties. Entanglement allows for quantum key distribution, QKD, a method of exchanging secret keys that is invulnerable to eavesdropping. In a QKD system, two parties create a pair of entangled particles and send one particle to each location. When one particle is measured, the outcome instantly determines the result of the other measurement, regardless of the distance between the two. This property allows for the secure exchange of cryptographic keys. Any attempt to intercept or measure the particles destroys their entanglement and reveals the presence of the intruder. This level of security is unbreakable by classical methods. Quantum communication also enables quantum teleportation, where quantum information, but not matter, is transferred from one place to another. Teleportation works by using entanglement to transfer the state of a quantum system from one location to another, without physically moving the system itself. While it doesn't violate relativity, since classical communication is still required to complete the process, it opens up new possibilities for instant communication across vast distances. Recent experiments have demonstrated quantum communication over long distances, including satellite-based entanglement distribution. The Messier satellite, launched in 2017, showed that entangled photons could be transmitted between space and Earth over 1,000 kilometers without losing their quantum correlations. This marks a monumental step toward creating a global quantum internet, where quantum communication would provide ultra-secure, tamper-proof data transfer that could reshape the way we think about privacy and communication in the future. The discoveries of superposition and entanglement are not just about building new technologies. They force us to reconsider the very nature of reality. Classical physics offers a picture of the world as made up of individual objects, each with fixed properties that evolve over time according to deterministic laws. But quantum mechanics upends this view. It shows that, at its core, the universe is governed by probabilities and relationships, not by fixed properties. Superposition tells us that systems do not exist in one state until they are observed. Instead, they exist in a superposition of all possible states, and only when measured do they collapse into a single state. This concept defies classical intuition. How can a system be in two places at once? How can it have multiple properties simultaneously? The answer lies in the quantum world's inherent uncertainty and the mathematical structure that governs the evolution of probabilities. Entanglement takes this even further, showing that particles can become linked in ways that cannot be explained by classical physics. When two particles are entangled, their properties are no longer independent. Measuring one particle instantly determines the state of the other, no matter how far apart they are. This phenomenon challenges our understanding of locality and separability, forcing us to rethink the very nature of space and time. The implications are profound. If reality is built on relationships rather than individual properties, then our view of the universe as a collection of separate objects is incomplete. Instead, the universe is a vast network of interconnections, where the state of one system is intertwined with the state of another, regardless of distance. This insight aligns with the mathematical structure of quantum mechanics, where the properties of a system are defined not by individual parts, but by the whole. The universe is not made of isolated entities, but of relationships that transcend classical notions of space and time. These revelations have led to new interpretations of quantum mechanics. Some physicists argue that the universe is fundamentally non-local, where events are connected in ways that transcend the speed of light. Others suggest that the true nature of reality is relational, where the very fabric of space and time is an emergent property of deeper quantum relationships. Yet, despite these different interpretations, the experimental evidence remains clear. The world operates according to the laws of quantum mechanics, and the strange behaviors of superposition and entanglement are not just theoretical oddities. They are the fundamental building blocks of reality. As quantum mechanics continues to shape our understanding of the universe, one central question remains: what does it all mean? Superposition and entanglement have led us to realize that the universe operates on a level far more interconnected and mysterious than classical physics ever suggested. The boundary between individual and collective behavior, between the microscopic and macroscopic worlds, is not as clear-cut as we once thought. Superposition and entanglement blur the lines between one system and many, showing that the relationships between systems are just as important as the individual properties of those systems. When two particles become entangled, they cannot be described independently of each other. They are part of a larger, unified quantum state. This realization forces us to reconsider what it means for something to exist. In the quantum world, existence is defined not by individual properties, but by the relationships between systems. Yet, despite this interconnectedness, there remains a boundary between the quantum and classical worlds. The quantum world operates according to probabilities and superpositions, while the classical world behaves deterministically with definite outcomes. This boundary is not a fundamental feature of nature, but rather a consequence of how quantum systems interact with their environment. Decoherence, the process by which quantum systems lose their coherence due to environmental interactions, explains why we experience a classical world despite living in a fundamentally quantum universe. This boundary, however, may not be as fixed as it seems. Recent theories and experiments suggest that the line between quantum and classical behavior might be more porous than we think. As scientists continue to explore the limits of quantum mechanics, they are discovering that the rules of the quantum world apply not only to microscopic particles, but to larger systems as well. Could it be that the strange, non-local behavior of quantum entanglement is not confined to small particles, but extends to the very fabric of the universe? Could the entire cosmos be entangled in ways we have yet to understand? The answers to these questions remain elusive, but one thing is certain: the journey into the quantum world is only just beginning. As we continue to unlock the mysteries of superposition, entanglement, and the quantum state, we will inevitably uncover new realms of reality that challenge our deepest assumptions about space, time, and the very nature of existence. The future is quantum, and the mysteries it holds are waiting to be discovered. And so, as we close this exploration, we stand at the edge of a new era of scientific discovery. The quantum world, with all its strange and mind-bending properties, is revealing itself not as a theoretical abstraction, but as a tangible reality that shapes the very foundation of the universe. What we uncover next may be beyond imagination, but it will undoubtedly be rooted in the quantum principles that have already begun to transform our understanding of the world.